So, having discussed finite automaton at a great length, let us look at properties of regular sets. So, what all we have seen so far is the following. Given a language which is a subset of sigma star for some finite alphabet sigma, when we say this language is regular, which means it is the following. One can construct a finite automaton. It could be a deterministic finite automaton, or it could be a finite automaton with epsilon or without epsilon, which means one can bring non-determinism over here. One can also come up with a regular expression which is a succinct way of representing sets accepted by or set of strings accepted by finite automaton, and they are all equivalent, meaning given a regular expression one can come up with an equivalent deterministic finite automaton, and given a deterministic finite automaton one can come up with an equivalent regular expression. Similarly, if we come up with a finite automaton with epsilon, one can come up with an equivalent DFA. So they are all equivalent. Now the question is, there are many L in sigma star, meaning there are many subsets in sigma star. How many subsets? Look at power set of sigma star. Now the question is the following, and look at L. There are many candidates for L, L1, L2, like this and so on. Now, our question is, to say that L1 is regular, you either come up with regular expression or a finite automaton. Similarly for each Li. But whether all of them are regular, or is it the case that some of them are not, meaning there are languages for which no regular expression exists and for which no finite automaton exists, which means they are non-regular sets. So now the fundamental question is, are there non-regular languages? One can look at it from two perspectives. Let's look at sigma. Sigma is a finite alphabet. It consists of some symbols, so A1 to AK. Now we talk about languages which are subset of sigma star, which means if sigma is finite, sigma star is countably infinite because it contains all possible strings over this. If you bring the theory of infinite sets that we discussed as part of discrete mathematics, you get to see that one can prove sigma star is countably infinite. Now, L is a subset of sigma star, which means ideally each subset is a candidate for regular. Instead of writing regular language, I am writing regular set. Each subset is a candidate for regular set, and that shows that how many subsets, number of subsets in sigma star is precisely power set of sigma star. Again, discrete max tells you that power set of sigma star is uncountable. since sigma star is countably infinite, power set of sigma star is uncountable. So there are uncountable languages in sigma star. Some of them are regular, some of them may not be. Okay, that there are non-regular sets, let's formally establish. So let me repeat this argument again. Sigma is a finite alphabet, which means sigma star is countably infinite. A language is a subset of sigma star, which means any subset you look for in sigma star is a candidate for regular set. Now how many subsets are there in sigma star? That's precisely power set of sigma star. If sigma star is countably infinite, then power set of a countably infinite set is uncountable. Through Cantor's diagonalization argument, one can show that power set of sigma star is uncountable, which means there are uncountable languages with respect to sigma. This implies that there are uncountable languages with respect to sigma. Okay. Look at from this perspective. If you know a language is regular, then one can come up with a finite automaton, a deterministic one or a non-deterministic one or a regular expression. Let's look at one. So one can come up with a finite automaton. Okay. So by definition, finite automaton implies finite number of states. Okay. So look at from this perspective. So sigma is finite. Okay. And number of states is finite. And each deterministic or a non-deterministic finite automaton, if you look at a deterministic finite automaton, then delta is a function from q cross sigma to q. If it is a non-deterministic one, it is q cross sigma to 2 power q. But sigma is finite, q is finite because finite automaton, finite number of states. So sigma is finite, q is finite, and so q could be a 2-state automaton on this sigma, or a 3-state automaton on this, or 10-state automaton on this, or 100-state automaton on this. So which means if you look at all possible functions, then are all possible DFAs over this, that is also finite. So number of possible DFAs is finite because sigma is finite, q is finite. Now number of possible DFAs with respect to q and sigma is a finite number. So which means, what is this telling you? You can list all 2-state automatons, all 3-state automatons, 4-state, 5-state, and so on, because q is finite. And if you look at all of them, if you count all of them, it is a finite number, which means number of DFAs possible for an alphabet like sigma is always finite in nature. This implies that number of, because for each DFA you can come up with a regular expression, which means the underlying set or set of strings or the underlying language is regular. So number of regular sets is finite. But we know number of candidates for regular sets is uncountable. So there is a gap. Number of candidates competing for regular sets is uncountable, but number of regular sets is actually finite, and which means there are many languages which are non-regular. There are many candidate sets in sigma star, they are non-regular. So from these two, one can conclude that there exists a non-regular set. So not all languages are regular, because number of regular sets is finite in nature, but number of candidates for regular sets is uncountable. So there must be a language which is non-regular. So this has given you an existential argument to show that there are non-regular sets. Now, how do we prove a language is non-regular, or how do you prove a set is non-regular? So let's have a closer look at how regular sets behave, or is there a pattern among regular sets? Probably that structural understanding will help us in proving that certain languages are non-regular. Okay. In fact, this was one of your assignment question, that sigma is ABC, and you are asked to list all 4 state DFAs possible over ABC. Similarly, one can ask all 5 state DFAs over ABC, all k states over this, and k is a fixed integer or a finite number. And when you talk about all possible DFAs, you take the union. Count all possible 2-state DFAs over sigma, 3 states DFA over sigma, like that over k-state DFA over sigma. Take the union. Each one is finite, therefore the union is also finite. But this is a much larger set, and because this has got mapping to the cardinality, this has got mapping to real numbers, therefore the cardinality of this set is same as the cardinality of real numbers, and thus we conclude this set is non-regular, and this set is uncountable. Since there is a gap between regular sets and number of candidates competing for regular sets, so naturally there must be a language which is non-regular. So now let's understand regular sets somewhat in a deeper sense, then we will get into examples using which we show that indeed there are non-regular sets. Consider a 4-state finite automaton So if you just look at this automaton without self loops and without cycles like this, so there are no self loops, there are no cycles like this. Okay, of course this is also a cycle, and so these two are not there. So which means if you start from this state, then the only possible string that it can accept is, suppose this one is say A, B, C, then it can accept ABC, nothing more. Okay, so it accepts a finite set. But the moment you bring a cycle, maybe a loop or something like this, let me say on A you go like this, and on on BC you read like this. Of course, there are other transitions from this. Now this tells you that one can read any number of BC followed by this, and after reading BC I can go over here and then going through this cycle multiple times, ABC, ABC, ABC and so on. Correct? So this tells you that things like this gives you many strings, and formally speaking it gives you an infinite set of strings. So a self loop like this or a cycle in the finite automaton is indeed giving you infinite set of strings accepted by the automaton. Okay, so that's one observation. So a loop or a cycle, presence of self loop or presence of a cycle gives you an infinite strings. Okay, and of course when I say presence of a cycle, when you pass a string and that string should involve a cycle, and finally it should take you to a final state. Okay, supposing you get to see like this. Okay. And then there is a cycle over here, and such an automaton is of no use. The reason is this part is finite and the cycle is actually over here, but strings generated by this will never take us to the final state. So such cycles we are not interested in. So when I say cycles containing final states, if there exists a string, on parsing that string starting from Q0, you should eventually go to the final state, and such parsing involves this kind of self loop or this kind of a cycle. If such a thing is there, then we say the underlying regular set is infinite in nature. Okay, so that's one observation. And another observation is the following. It is a 4-state automaton. For a 4-state automaton, you consider strings of length, say 3. So now you see that you may just go over this, and then if you just go over this, say 3 B's or 3 C's or B followed by 2 C's, you will continue to stay here. But there is one 3-length string that will take you to the accept state. Okay. And look at 4-length strings. So what is that I am trying to say is the following. You have a 4-state automaton and you look at strings of length 4. If you look at strings of length 4, and now let's focus on not just the strings that are accepted by the automaton. Okay. So what we will do, let me talk about regular strings. When I say regular strings accepted by this automaton. So you consider regular strings of length 4, which means strings accepted by the finite automaton. So it is length 4, which means you go through this loop once and read B or C followed by ABC. Okay, but if you read ABC followed by A, that string will not be accepted by the automaton. So similarly, look at regular strings of length 5. You may go over this twice and followed by this. Okay, but if you take ABC followed by A followed by B, then it will not be accepted by the machine. Look at this. And in this case, it could be ABC followed by again ABC, or you can go over this thrice followed by ABC. So now this clearly tells you, if you look at 6 length strings for this 4-state automaton, and there are strings accepted by this machine going through this loop or going through this cycle. Now the interesting part is the following. You can look at B plus C or B plus C or B plus C followed by ABC. Okay, or it could be ABC followed by ABC. Correct? So now for 6 length it is ABC followed by ABC. In general it is ABC followed by ABC star. In general it is B plus C star followed by ABC. So what is that I am trying to pitch in is the following. If you choose a string whose length is more than the number of states, then you must find a substring which you can loop over, which will kind of get into a cycle, and one can go through that multiple times. In this case it is ABC star, in this case it is B plus C star. And with this one can generate 7 length, 8 length, 9 length. With this again one can generate 9, 12, all that. So with just one pattern one can generate more. That's the second property.